Hello, today I'm going to be discussing Halide for high performance computing. So what is Halide? Halide is an open source functional language embedded in C++ and made by MIT in 2012. It allows the separation from the schedule of an algorithm and its computation. Because of this, it allows for easy portability whilst maintaining efficiency. For example, if we move from one machine to another, it is more than likely that we'll need to change the schedule as well as the amount of threads used to run optimally. Halide allows this to be done easily. Additionally, Halide allows the user to specify the granularity as well as the schedule to use when using an algorithm. Because of this, it allows the user to test a greater number of possible setups quickly and easily. Finally, it removes convolution, which can occur from adding parallelism to an application, making it more readable, understandable, and less prone to errors. So what is the main focus of Halide? Halide's main focus in development was image processing, as many packages struggled to combat the issues of loading and storing data, something that Halide aimed to fix. Halide also aims to keep the computation local to each thread, meaning that data does not need to be stored and can instead be used immediately, resulting in great locality. Finally, Halide should no longer be thought of just an image processing package, but instead thought of it as a data-specific package, working with data structures such as multi-dimensional arrays, regular grids extremely well. So what are the findings of the paper? Halide was stated to reduce convolution of parallel code, and looking at the below code snippets, we can verify this. The code input is an image, the output being a blurred image. We first take the horizontal and the vertical, and we blur them, adding x minus 1, x plus 1 divided by 3, and then using those values as y minus 1, y, and y plus 1 divided by 3 to blur it. This is the non-parallel version of C++, which takes considerably longer than either the C++ parallel version or Halide, with taking 6.5 milliseconds per megapixel. The C++ version, which is parallel, we can see is very much convoluted. We can't even see the computation of BH or BV anywhere within it. Because of this, it would be very, very difficult to not create errors. Finally, if we look at Halide, which takes about the same time as the C++ version, if not better, only taking 0.29 milliseconds per megapixel instead of 0.30 milliseconds per megapixel, we can see BH and BV calculations already there. The only thing that is different from the serial version to the Halide version is the removal of the for loops and the addition of the tile function and parallel number of threads. So what are the different types of Halide scheduling? Well, there's three main different types of Halide scheduling type: inline, compute root, and compute at. Inline is the most parallel of all three, taking a frame size of 3 by 3 and giving it to each thread to process and calculating 1 BV for that thread. It does this in a clean manner using the value of BH as soon as possible, creating good locality. However, if we look at the process more deeply, we notice there are many recomputed values. Consider the case we would like to work out this blue value here in BV. In this case, we have already calculated the one above that has used all of these three values of BH. If we look at the calculation of this blue value, it uses this blue value, and this blue value, but because it's on a different thread, it will have to calculate these two blue values again, meaning that it has major recalculation costs. However, as stated previously, it has very good locality and high parallel opportunities. The next one is the compute root scheduling type. This is completely serial and therefore has no recalculation costs. It also has no parallel opportunities because it's serial, and it has bad locality. This is due to the fact that it calculates the full BH first and then the full BV second. Finally, the compute at scheduling type sets the BV tile size. So the BV tile size is how much work we want to assign to each thread. For example, in the bottom right input, we see that we have set a tile size of 5, meaning that each thread is tasked with calculating a 5 by 5 grid of BV. This obviously means that we have recalculation cost shown by the dashed lines in each grid. We would need 4 of these grids to satisfy the whole grid, as only 2 are shown in the image. This obviously has a dynamic recalculation cost and a dynamic parallel opportunities, as we can increase or decrease the BV tile size to alter both of them. Because of this, it has the chance to have great locality or good locality or terrible locality, depending on which choice is chosen. So, what are the different types of halide scheduling underneath that? Well, there's 6 different types under arcing, and they are split into 2 sections, non-parallel and parallel. The non-parallel versions have 3 major types: row major, which works on lines, column major, which works on vertical axis, and then tiled, which has a bit of both. We also have parallel algorithm or parallel scheduling types, such as vectorized, parallel, or parallel tiled. These are very similar to the serial versions, the row major being very similar to parallel, the tiled being very similar to parallel tiled, and the vectorized being very similar to a mixture of row major and column major.
The compiling procedure of halide includes 4 phases. First of all, the compiler takes a graph of the function and lowers it to imperative code for a variety of architectures. Then, this code is converted to LLVM's intermediate representation, and this generates the machine code. The lowering procedure is directed by the schedule, and the way that it's designed makes it controllable and deterministic. The 2 important responsibilities of lowering is synthesizing the loop nest specified by the schedule, and the second one is inferring the regions of each function that must be computed to satisfy all producer-consumer dependencies. Also, the lowering could implement passes for tracing, profiling, and similar instrumentation, or to apply opportunistic optimizations. Halide has been compared with the equivalently fastest codes to some applications, and it goes more concise and faster than them. One application that halide has been applied is bilateral grid, which smooths an image while preserving its main edges. It goes much faster than the equivalent of C++, and the lines of code that used were less. In order to achieve this performance, it sacrificed locality to reduce overhead and used tiles fusion to improve locality through blurring steps. Another application that halide was tested is local Laplacian filters, which tones map images and enhance local contrast in an edge-respecting fashion. As you can see in the image, halide was much faster than pure C++ version with IPP or OpenMP. Also, in fast Fourier transform, which implements small 2-dimensional fast Fourier transforms based on an algorithm adapted for GPUs, fast Fourier transform in West software took thousands lines of code compared with halide's code, which was only 350 lines. Except for this, halide improved locality and could easily modify it. Finally, halide applied to camera pipeline, which transforms the raw data recorded by a camera sensor into a photograph. The halide code was much faster than optimized assembly and more concise.
This brings us on to issues in future research. Currently, there are 2 issues with halide that are mentioned in the paper. The first issue was modularizing schedules without sacrificing performance. This is apparently still an issue with halide. Another issue was that it's apparently challenging for novices and those unfamiliar with high-performance programming to master. Both of these issues can be resolved using automatic scheduling, which is still being made and verified that it works. However, it has been very promising, apparently. So the automated scheduling that we were just talking about has been done in 2 steps so far. Initially, they used to try all of the schedules that could be possibly made, which was an exponentially large amount of them. They then ran these all on benchmarking software, which was apparently difficult to use and it wasn't scalable the way they were doing it. However, afterwards, they decided to start using search heuristics to reduce the search space of possible schedules. Instead of analyzing the benchmark results, they now start to analyze the algorithms instead of them. This makes it easier to use and more scalable.
We read 2 further articles about highlight. First one, parallel associative reductions in highlight. This article describes a new highlight supports the same scheduling for reductions, which traditional highlight doesn't support. Second one, Polyimage, automatic optimization for image processing pipelines. This article presents the design and implementation of a domain-specific language along with its optimizing code generator for a class of image processing pipelines.
Thank you for your attention, and if you have any other questions, feel free to get in contact.